All right, everybody, this is the advanced study assignment for experiment 20, which is the iodination of acetone. So we're going to go through the advanced study assignment questions for this lab. So the first question involves this reaction mixture here, which is 5 milliliters of acetone, 10 milliliters of HCl, and 10 milliliters of iodine. So that's a total of 25 milliliters of reagents. We're adding an additional 25 milliliters of water to bring that total volume up to 50 milliliters. So the first question that we're going to answer involves this particular mixture. Okay, and we want to start by finding the moles of acetone that were in this reaction mixture. Okay, if we want to find the moles of any of the reagents that were added to the mixture, we have to look at our initial molarity and our initial volume to find this information out. Okay, the initial molarity and the initial volume will tell us how many moles of that reagent are present. So for the moles of acetone, we're going to take our 5 milliliters and convert it into liters, then multiply it by the molarity, and we have 0.02 moles of acetone in that reaction mixture. Now the second part of this question is to find the molarity of the acetone in the reaction mixture. Molarity is just moles divided by volume in liters. Our total volume here is 50 milliliters, which is 0.05 liters. So the molarity of our acetone in the reaction mixture is going to be 0.4 molar. Okay, now we want to ask ourselves how we could change that reaction mixture just a little bit. Now we want to double the molarity of the acetone in that reaction mixture, but we still want to keep our total volume at 50 milliliters. And we do not want to change the concentration of our other components. So our hydrogen ion concentration should remain the same, and our iodine concentration should remain the same. So we have to ask ourselves where these components are coming from, right? We know that the acetone is coming from that 4 molar stock solution we had. The iodine is also coming from the stock solution. Where is the H plus coming from? That is coming from the HCl. Okay, some people are tempted to assign some H plus value to the water that's present in the solution, but that water is just there to maintain a total volume of 50 milliliters. It's not actually taking part in the reaction. So how can we double the molarity? What is the first thing that we have to do? We have to double the number of moles that are present. How can we double the moles? Well, we can double the volume of the acetone that we add, because we know based on our standard equation that molarity times volume is moles. So how do we maintain a volume of 50 milliliters then? Well, if we're going to double the volume of the acetone that we add, that means that we're going to have to keep a constant volume of 50. So we will decrease our water volume to 20 milliliters to make up for the extra 5 milliliters of acetone that we'll be adding to our mixture. Now let's use this information to calculate the rate of the reaction. All right, so we're going to look at equation 5 here, and that says that rate equals the initial concentration of iodine divided by the time it took for the iodine color to disappear. And here we see that that is 510 seconds. Okay, before we can solve this, we're going to have to find the concentration of iodine in the reaction mixture. Remember that concentration equals molarity, and the molarity is going to equal the moles of iodine divided by the total liters of the solution. So to find the moles of iodine, we will do the molarity of the iodine times the volume in liters. That's this calculation here. And we get 5.0 times 10 to the negative 5 moles of iodine. Then to find the reaction molarity, we'll take that mole value and divide it by our total volume in liters, 0.050 liters. And this is our concentration of iodine in the reaction mixture. And that is the value that we will plug into equation 5. Okay, equation 5 should be using a molarity value. So we'll take that molarity and divide it by our time in seconds, And that gives us a rate for this reaction of 2.0 times 10 to the negative 6 molarity over seconds. Okay, now we want to look at the information that we have. Okay, we found out the rate now. We know how to find out the initial concentrations of everything. And now we want to write everything out that we know up to this point. Okay, so we have to do one more calculation to kind of complete the information that we have available to us, because we found like the concentration of acetone and iodine, but we haven't found the concentration of H plus yet. So we're going to take a minute to calculate that out. We'll take the 10 milliliters, convert it to liters, multiply it by the molarity. That gives us the mole value. We will take that mole value and we will divide it by the total volume in liters, and that is the concentration of the hydrogen ions. This is our rate expression. Okay, so now we are going to actually plug in all of the values that we know up to this point and see what we do not know. Right, we solve for the rate, so we know what that is, and we have concentration values for each of our reactants. So what are the unknowns that still remain? We don't know the K value yet. We don't know the orders of the reactants yet. So we're going to focus in on how we solve for these orders of the reactants. And we're going to start here by making up a second reaction mixture. And what we're going to do here is we are going to change one of the components. Okay, you're going to notice here that the volume of our HCl has changed. So the first thing that we need to do is figure out what the initial concentrations of each component are in this new reaction mixture. Well, the only concentration that's different is the concentration of the HCl. Acetone and iodine are still the same, so their concentrations will mimic that last reaction that we just looked at. The volume of the HCl has doubled. That means there's twice as many moles in the same volume. That means that the molarity of the H plus has doubled. So it's gone from 0.20 molar to 0.40 molar. And our acetone is still 0.40 molar, and our iodine is 0.0010 molar. Okay, and these are the values that we're going to use to find the rate of our second reaction mixture. And we are still going to use that same equation 5, where we have the initial concentration of iodine divided by the time. That will give us the rate of this reaction. Now that we have two rate values, we can start looking at the orders of the reactants and solving for them. Okay, I'm writing out the rate expression here also, because this is the rate expression that we're going to use to figure out those order values. Because to solve for the order, an unknown order value, we need to divide two rate expressions. Okay, so in this case, we have rate expression 1 and 2, and it doesn't matter which one you divide by the other. I like to set it up so that I get whole numbers back out when I do my division instead of decimals. So I'm going to take the entire rate expression 2 and divide it over the rate expression 1, and I'm going to eventually isolate P. So this is what that looks like. This is rate 2, and these are the concentration values that correspond. This is rate 1 and the corresponding concentration value. Now I'm going to cancel everything out that's the same. Okay. So you see the concentration of acetone is the same, so it cancels out. K is the same, so it cancels out. M cancels out. Iodine cancels out, and N cancels out. So I'm only left with 0.40 raised to the P divided by 0.2 raised to the P equals rate 2 over rate 1. So now I'm going to solve that down a little bit further. And I'm left with this. 2 equals 0.4 over 0.2 raised to the P. And now I just have to isolate P and solve for it. Okay, so I'm going to do my division in the parentheses, and I get 2 equals 2 to the P. And you might be able to figure out P just from looking at this expression, but if you wanted to see how to mathematically solve for the exponent, you'd want to use your log rules here, okay? Using your log rules would pull that exponent off and bring it down into your main number line here. So you take the natural log of 2p, and that's going to equal the natural log of 2. You can use log or natural log. I just like natural log better. And now you're just going to isolate p. Okay, so this is the stepwise process here. When you take the natural log of something with an exponent, the exponent gets pulled off and put in front. Then you can divide this side by the natural log of 2, and you can divide this side by the natural log of 2. What you end up with is p equals 1. So what does that mean? It means the reaction is first order with respect to the hydrogen ions that are present. And now our final question, we have a third reaction mixture that was made up. And we have 5 mils of acetone, 20 mils of HCl, and 5 mils of iodine. If the reaction is 0 order in I2, how long would it take for the I2 color to disappear at the temperature of the reaction mixture in problem 3? What does a 0 order reactant mean? When you have a 0 order reaction, your rate is independent of the concentration of the reactant that you're looking at. What you have to remember here, though, is that rate is not the same thing as time. So just because the rate is the same does not mean that the time is the same, okay? A rate is something that is measured per unit of time, something like the speed of a car. So if you're going 60 miles per hour, that's your rate of speed. Okay, but say your car goes 60 miles an hour and you have to go 5 miles versus a trip that will be 100 miles. That 100-mile trip will still take more time than your 5-mile trip, even though you are traveling at the same rate. And that's what's happening here. So we have to figure out how long this reaction will take if we have as much iodine as is present in this reaction mixture, this 5 mils of 0.005. Luckily, we have an equation that relates the concentration of iodine, the rate of a reaction, and time. So we can solve equation 5 for the time variable instead of the rate variable. Let's do that. Oh, well, I guess we do need to find the concentration of iodine first. So let's do that. We'll take the moles of iodine, which is your volume times your molarity. We'll divide it by our total volume in liters, and we have our molarity here. That will be the molarity. This is the initial concentration of the iodine, and that's what will go into equation 5. Now we'll take equation 5 and we're going to solve it for time instead. Okay, you might be asking, well, where do we get this rate value from? Because we already found the rate in the previous reaction for a solution with 5 milliliters of acetone and 20 milliliters of HCl, we can use that same rate and apply it to this reaction mixture, because the only thing that's different between that reaction mixture, that second reaction mixture, and this third reaction mixture is the volume of the iodine. And iodine is a 0 order reactant, so the change in concentration here won't affect the rate of the reaction. So we can use that rate and we can plug it in right down here. We can use that initial concentration of iodine, plug it in up here, and we can solve for the time it would take for that iodine color to disappear. Okay. That's the end of the advanced study assignment. These are the post-lab questions that are on your data sheet that we will expect you to answer in your post-lab reflection this week. If I were you, I would take note of these questions. And when you open the link to the procedure video for experiment 20, you should be considering these questions while you're watching that procedure video to try to help you answer them.